Thank you very much for giving me the opportunity to talk here. I would like to talk about the very concrete structure. This is related to the algebra structure and pre-mutli simplex structure. And I talk about application to physics. The purpose is to generalize so-called twisted Poisson structure to higher structure. And another purpose is to generalize so-called AKSZ sigma model. This is a very beautiful sigma model constructed from the so-called Q-manifold and the geometric structure. So, but the BV formalism is more general than AKSZ. So we want to generalize such a beautiful structure to more general BV formalism. And to do is we consider algebroid and pre-mutli simplex structure, and we consider some compatibility. This gives some maybe beautiful structure. So the plan of talk is following. First, we analyze some geometry on the algebroid with multi-simplex manifold, and the next we discuss about the graded geometry interpretation, the description of this geometric structure, and finally we consider some sigma model in higher dimensions. First, I want to prepare some geometric structure. First one is the algebroids. Maybe many people already know the algebroids, but I wrote some notation, the definition of the algebroid to fix notation. But the algebroid is a vector bundle E over M, and it has two operations. One operation the bundle was so-called called anchor map row, and second operation the Lie bracket. And the consistency condition is this Leibniz rule. There is some we wrote some. I wrote some examples of the algebroid. Okay, I explain only the third example, the action algebroid. We assume some algebra action on manifold M. If there is a algebra action, Lie group action, we can obtain algebra action to M as a infinitesimal action on M. So this action induce some bundle map on trivial bundle M times K to tangent bundle. This is anchor map. The consistency of Lie bracket requires the row must satisfy this condition, homomorphism condition. Such action induce some algebra structure on trivial bundle M times K. This is called action algebroid. Another structure is so-called Lie Algebraic Differential. We consider exterior algebra on E star, and we consider space of section on this exterior algebra space. We call this space space for E differential forms. On this space, we can define some differential. It is a generalization of so-called Chevalier-Algebroic differential. The definition is like that. We can easily check this differential, the square of this differential equal to 0. This is the Lie algebroid differential. And we consider n-prefix structure. This is closed n+1 form omega. If manifold M has a closed n+1 form omega, this is called a pre-n-prefix manifold. A pre means that we don't assume non-degeneracy of this n+1 form. So this is pre-n-prefix. Of course, one prefix structure is a symplectic structure. We consider some compatibility condition of two algebroid and pre-n-prefix structure. First, we prepare notation. This is the interior product, k times interior product of with rho and omega. This is definition is concrete definition is the last part. This one, we consider contraction on Tm plus and T star m, and k times rho and omega. There is some other notation of this operations. We use some other notation also, and we consider some compatibility condition. In my talk, we use only this one equation. We analyze only this equation. This equation is as follows. Let E be a algebroid on a pre-n-prefix manifold M. We prepare n+1 form, closed n+1 form omega, and En form J. We prepare En form J. This J satisfy, if J satisfy this equation, J is called compatible with the algebraic structure and the pre-n-prefix structure. First, we check the consistency with d square equals 0 condition. So this equation is, for the consistency of this equation to this equation, this equation must be satisfied. But this equation is satisfied if omega is closed and this homomorphic condition is satisfied. This equation is satisfied if these two equations satisfied. On re-algebroid case, this homomorphism is a homomorphism condition of anchor map. This is satisfied, and this is the condition of the pre-n-prefix manifold. So in our setting, this condition is consistent with the other structure. But we can consider more general algebroid such as almost re-algebroid. This is and the Coulomb algebroid and so on. We consider example of this structure. I talk about the first one is the twisted Poisson structure. Twisted Poisson structure is like that. We assume by vector pi and the closed 3 form H. If to pi and H satisfy this structure, this equation, it is called twisted Poisson structure. Where the S bracket is the so-called Schouten bracket. If for the twisted Poisson structure, we can construct the algebroid on the cotangent bundle. This is obtained like this. The anchor map is the so-called musical homomorphism defined from the bivector pi. This is the anchor map, and the Lie bracket is defined like this. It is the kind of the H deformation of the so-called causal bracket, like this. So two operations satisfy the definition of Lie algebroids. So we can define Lie algebroid on T star M. And okay, this equation 2 is under this Lie algebroid, this equation is related by this equation. This is the Lie algebroid differential induced from this Lie algebroid structure. So we can find that the J equals pi. And the pi is nothing but compatible E2 form. Right? And with the pre and duplex form, omega equals H. The second example is the twisted R Poisson structure. It is the considered by Thanasis. We consider that the pi is a bivector field. It is. We assume this is Poisson bivector field. It means that Scouten bracket pi and pi equal to 0. We assume this one, and we introduce the closure n plus 1 form H, and we consider R. R is n multivector. This is the element of section. This bundle. First, the Poisson structure defines the Lie algebroid structure on cotangent bundle. This is in special case of this case, and where the H, if we H equals 0, this is the Poisson structure, and we can define Lie algebroid on cotangent bundle. So we can define cotangent bundle on the Lie algebroid structure on cotangent bundle. So we can define the Lie algebroid differential on this space. And the Poisson bivector, the HR, twisted R Poisson structure. Definition of twisted Poisson is as follows: if pi R H satisfy this equation, this is called this triple is called twisted R Poisson structure. But we can rewrite this equation to our form. We can rewrite this equation to like this by using the algebraic differential. So it means R equals J, and H is the pre-mutli form omega, like this. So this is the example of our structure. Another example we consider, I say another example. This is the momentum map. In the simplex geometry, momentum theory is very important. Momentum map theory is like that. M omega be a simplex manifold. It means n equals 1 in our setting. And we consider Lie group action on M. The action induces it is the same setting of with the sorry of with the action Lie algebroid structure. So we can construct action Lie algebroid from this Lie group action. Action is like this. Yeah, Lie algebroid action. From Lie algebroid action, we can construct anchor map on trivial bundle. And since we have trivial bundle, we can on the momentum map is the map from M to K star, but it is regarded as the section of on dual bundle. This like this. M to dual section of dual bundle. And a momentum map mu 0 is, and this is a momentum m to the map m to K star. If mu 0 satisfies two equations, this is the mu, essentially mu 0 is Hamiltonian for the action law. And this second equation is the equivariant equation, right? This is the momentum map. If two equations is satisfied, the mu 0 is a momentum map. But momentum map equation is rewritten like this equivalently. Under the first equation, second equation is rewritten like this. You can check. Yeah. So second equation is nothing but our equation 1. So I mean that the mu 0 is equal to j on with n equal 1 simplex manifold. Mu 0 is a compatible E1 form on simplex manifold. Equation Yotaro only one, yes. This one. First, the definition. This one. Yeah. No, not related to this person. Yeah, and generalization of momentum map to multi-simplex manifold is proposed in some. There are many proposed to of momentum map. Generally, there are many proposed of generalizations of momentum map to multi-simplex manifold. One was proposed is a homotopy momentum map. So I explained homotopy momentum briefly. In this setting, we consider any predictive manifold, right? The omega is any predictive form. And we assume that some realizable action on M. And we consider a series of the mu 0 form to n minus 1 form, the series of the differential form, taking a value of the wedge product n minus k wedge product of k star. If this mu satisfies this equation, and this is called the homotopy momentum map, where the D is the usual drum differential and DCE is a Algebraic differential on the algebra. D is a drum differential. The exterior, yeah, and it's a generalization to exterior. This is a trivial bundle. So yeah, we can take the flat and the trivial connection. Yeah, precisely, yes. Yeah. Then, anyway, it is and we see 0 form part mu 0 in this the definition, and we should rewrite in properly using some other equation. This is the series of equation, right? We can divide this equal equation to each form. So we can we obtain the series of equations that we can combine the equation. So we obtain the equation to 0 form part. So 0 form part equation is rewritten like this. So this equation is nothing but our condition for the compatible condition for the multi-symplectic form, the n-plectic form and the realgebroid structure. So this is the J equal minus mu, and this is the compatible En form. We have there is a proposal to the moment map and the generalization of moment map to realgebroid setting. This is the so-called momentum section. In this momentum section is also example of our structure. We consider some pre-symplectic manifold. Omega is 2 form, closed 2 form. And we consider vector realgebroid on M, E, realgebroid E on M. We have to introduce some connection on E. This connection is a normal connection, right? If the section of E star is section of E star is called a momentum section if these two equations is satisfied. Two equations are satisfied. And the second equation is nothing but our the compatible condition. And this is for n equal 1 and m equal j. So this is the example of our structure. And we can generalize this. There is a proposal to generalize momentum section to some multiple simplex manifold. There is in this case, even in this case, this is similar to similarly to momentum homotopy momentum section case. We can check that the zero-form part is satisfied the compatibility condition equation 1 like that. Okay. Yeah, from that, we analyze the some graded manifold description of this structure. Graded manifold description is directly related to so-called AKSZ sigma model. So we want to write some sigma model. So we rewrite such a equation 1 to the Q-manifold structure, right? First, this is a definition of Q-manifold. We consider graded manifold. I don't explain graded manifold no more anymore. So we consider a non-negatively graded manifold, so-called any manifold. If any manifold M has a vector field Q of degree +1 satisfied Q square equals 0, it is called Q-manifold. So we want to construct Q-manifold corresponding to the compatible EN manifold, EN form. In order to describe as Q-manifold, we consider cotangent, shifted cotangent bundle of the realgebroid E, like this. N-1 shifted cotangent bundle. And we introduce local coordinate like this, xazy of degree 0, 1, n-1, n-2. This is the local coordinate of this one. And this is the bundle, local coordinate bundle, and this is cotangent direction, coordinate on to cotangent direction. And we consider local coordinate expression of rho j, h, and bracket. Partial derivative. This partial derivative xi derivative, x derivative with respect to x. This is sorry, this is the typo. Sorry, this type. Yeah, sorry. Yeah, this is the no partial derivative. This type. Yeah. the Q, we can construct a Q operation like this, concretely construction. So we can prove that the Q square 0 equal condition is equivalent to the condition of the compatibility EN form. J is compatible EN form and the algebroid E. That this Q square equals 0 condition gives the simultaneously algebroid condition and compatible condition. We want to construct QP manifold, but yeah, in this J, we have J like this. In this case, the first part give the first line give the algebroid. So yeah, there are more general possibility, but we consider only the algebroid case. So we can generalize. We can consider more general case. But we now in this talk I concentrate on the algebroid. Yeah. First part is the cotangent list. Yeah, if J and H equals 0, it is cotangent. Yeah, you are right. If J and H equals 0, this is cotangent drift. Yeah. Yeah, but twisted, but we choose some special twisting. Yeah, not all general twisting, not all, not most general. In order to construct AKSZ sigma model, we need QP structure. QP structure is if n manifold M has graded simplex form of degree n, and the vector field Q of degree +1 satisfying Q square 0, this is the same Q structure, but such that this condition, this compatibility condition, if this compatibility condition is satisfied, this is called the QP manifold. On the QP manifold, we can, and degree is non-zero. We can there exists a function, Hamilton function for Q, like this, and the Q square equals 0 condition is equivalent to this condition. If we can construct QP manifold, we can construct the AKSZ sigma model easily. There is a formula. But if H is non-zero, the previous Q, if we choose previous Q, and this is the cotangent band, so we can consider canonical simplex form of degree n. If we choose canonical simplex form and this Q, we choose this Q, but in this case, this equation is not satisfied if H equals non-zero. So there is no general method, general formula to construct the QP manifold in this structure, right? Only in special case we can construct QP. So we have to consider another method. We have another interpretation as a higher Dirac structure. There are many people consider some higher generalization of the Dirac structure. This is a canonical simplex form on this cotangent bundle. First, we choose this canonical simplex form, right? And we forget this Q structure. It is not consistent with this equation. So we forget Q. But we can consider a consistent QP structure with this canonical simplex structure like this. At first, we forget J. Only we consider anchor map, and this is the structure function of Lie bracket, and this is the closed n+1 form. So sorry, n+1. This is the typo. We consider this Hamiltonian function. If we consider this Hamiltonian function, then to impose this condition, this is a defined QP structure, and this QP structure is we can confirm that this QP structure equivalent to the E is Lie algebroid. This is satisfied if E is sorry. Okay. Yeah, we obtain H equal DH equal there. Yes. H equal rho. Sorry? Yes. Okay. This is direction. This one. This is if this the equation satisfied, we can consider this one. But yeah. So this direction is not necessarily satisfied. Yeah. Right. The observation is that the algebraic structure and DH equals 0 structure is gives this QP structure. Yeah. In order to describe our structure as a higher Dirac structure, we prepare so-called Lie n algebraic structure on this bundle, generalize in this generalized bundle. This bundle is a kind of generalization of Coulomb algebroid. So this bundle has three operations, some kind of three operations. Is a symmetric pairing on the section for the section at this time. Sorry, and the row is anchor map, and this is a higher Dorfman bracket. This is the bilinear, so-called bilinear bracket on the space of section. That we need some consistency condition of the identity of three operation. That this is the constructed from the QP structure like this. We can correspondence. We have correspondence of this bundle to the graded manifold like this. And simply speaking, we choose some basis of the bundle. This is the bundle. Basis is this is the coordinate on M, and this is the basis of the E star and E and the code basis of Tm. This is replaced to the graded coordinate by shifting grading like this, x, a, y, z. The three operation is computed from this derived bracket. This is a so-called derived bracket construction of Lie and algebroid. The t theta is QP Q and the Hamiltonian function of QP manifold. This bracket is graded Poisson bracket constructed from canonical graded simplex form. So we obtain that this operation, the identity of the three operation is obtained from this Hamiltonian function condition of Hamiltonian function. So we can construct the Lie algebroid, and this is the concrete operation of the three operation constructed from the QP manifold structure. And this is inner product of. This is first one is obtained from inner product of E and E star, like this. Then the second one is the anchor map. The third one is a higher Dolphin bracket, like this, where the differential is so the algebraic differential, like this. And we want to introduce J in the section En form in this structure. In order to introduce J, we have to consider higher, so-called higher Dirac structure. Definition of higher Dirac structure in my case is like this. Higher Dirac structure is a bundle L of the Lie and algebroid. This satisfy the condition symmetry bearing is equal to 0 and the Earth. And the Dolphin bracket is involutive. This is the definition for general Lie and algebroid. In my definition in this talk. Right? Most general, yes. E is a Dolphin bracket, higher Dolphin bracket. Constructed from the derived bracket construction, this one. That if we have QP manifold and we can construct this operation by this formula, the derived bracket, so we obtain this is definition of higher Dolphin bracket in my case. Then we impose two conditions. This one and this one. Yeah, so I don't impose some maximal condition of rank. The Lagrangian Q-manifold. Yeah. Different. Okay. Okay, yeah, this is okay. This is Lagrangian Q-manifold. So in my talk, we use this structure. Yeah. So we define the section this bundle like this. The U plus JU. This is the section of this bundle for arbitrary the section of E UU. if we impose two condition. If we impose this condition, this is equivalent to our equation 1. If and only if Lj is this higher Dirac structure and the Lagrangian Q-manifold, right? So this is another interpretation of these equations. The last part is the construction of the so-called topological sigma model, which have the geometric structure I discussed. In the T star M, cotangent boundary case is constructed by Thanasis, and my case is for general algebroid case. First, we explain action function, so-called action functional. Sigma model, we consider sigma model. So we consider n+1 dimensional manifold sig Z with n-dimensional boundary sigma. And we consider map from Z to M, this one. This M is we consider algebraic structure algebroid E over M, and moreover we consider M is a pre-elliptic manifold, and the existence of the compatible EN form. We have two pairing of this pairing, Tm and T star M and E star, like this. And we introduce the classical field A, Y, Z corresponding to the coordinate of the Q manifold, right? This is we have two coordinates on this one, and this is corresponding, but it is not precisely not the same. It is only the classical part. This is n-1, sorry, this is typo. The action function is as follows. First term is the pairing of Z and dx, and the second term is pairing of Y and dA. And third term coming from anchor map, and this fourth term is coming from the Lie bracket. And this term is constructed J, pullback of J. And the final term is the so-called Bessel-Minor term. This is the pullback, integration of pullback of the H. This is the action functional. So if H equals 0, this action function coming from the so-called AKSZ sigma model, special case of AKSZ sigma model. But if we have non-zero H, it is not AKSZ. So we have to we have to analyze carefully this model. We check the consistency, physical consistency as a physical model. This completely consistent physical model. First, we analyze Hamiltonian formalism. So we take the sigma to this manifold. R is time direction and Tn is space direction. Sorry, Tn-1, this one. And Hamiltonian is constructed by so-called Legendre transformation of Lagrangian. Lagrangian is an integrand of the action functional. And this is the all fields. First, we can we consider normal procedure of the mechanics. First, we consider canonical conjugate momentum and Poisson bracket. Poisson bracket is the same as the AKSZ. Poisson bracket is constructed from simplectic form, but simplectic form is the same as the AKSZ PF case. This is this zero is the restriction to the classical field, and we drop all the ghosts and the anti-field. Then in order to consistency, this theory has a so-called constraint. Constraint is a generation. The constraints mean we will consider some generator function and the space of generator function to generate the algebroid action, as a Poisson algebra. Last sentence. Sorry, so it's not so. Yeah, the constraint. This is structure of this theory has structure of algebra. So this is structure. The algebra structure is realized as a Poisson bracket of the constraint. So I want to say like that. No. I assume the algebra structure. And the constraint algebra, the algebra structure. I assume the algebra structure, and from the algebra structure, the Poisson bracket must have some condition. This is of the constraint. Sorry, we go. I explain the next one. And it means some the Hamiltonian generate time evolution of the mechanics. So time evolution must be consistent with the algebra structure. The algebra structure. I want to say like that. Okay, and anyway, in the normal mechanics system, this theory has a so-called constraint. Constraint means that some The space of constraint, constraint must be consistent with the Hamiltonian Poisson bracket. So this condition is like that. That the Hamiltonian H is Hamiltonian Poisson bracket Hamiltonian, and the constraint space of constraint must be included in the space of constraint, and the space of constraint must be involutive. This is two conditions must be satisfied. So in this case, the basis of constraint are called the first-class constraint. So a normal procedure of Hamiltonian mechanics, we can construct the Hamiltonian like this, and where 3G is like this. We can concretely compute the three constraint equation. This is so-called constraint generating the algebroid. So first we assume the algebra structure on rho and C, but we don't assume the condition of J. So we impose this involutive condition So if we impose two conditions, we obtain the following theorem. We assume the E is a Lie-algebroid, so it means the rho is anchor map and the C is the structural function of Lie-algebroid. We assume this one. Then we assume H is a pre-mutli form. It means the H is closed. We assume H is closed. Then the space of constraint is satisfied to condition if and only if J is compatible EN form. This is the result. So this how many? Yes. Yeah. I assume for it is for simplicity. Yeah. So this compatible condition is consistent with this mechanics of this classical action. So we can see that the BFB formalism works. It is a concrete the Poisson bracket of each constraint. This Poisson bracket is rather complicated, but we can anyway compute, and then we can concretely confirm that this is in fact involutive. And we can consider Lagrangian formalism. In Lagrangian formalism, we have to check the consistency of gauge transformation. Gauge transformation is constructed from this constraint like this. There is the typical method to construct gauge transformation anyway. And the consistency condition is like that. Gauge transformation over the action functional must be equal to 0, and the algebra of gauge transformation must be closed. And this is the simple equation, but the second equation is not so simple. This equality is up to equation of motion. It is enough, sufficient to satisfy this equation up to equation of motion. Though this is saturated so of the difficulty of mechanics system. So this saturated is solved by the so-called BB formalism. But we don't have BB formalism yet, so we have to compute this some computation. So we need 3 gauge parameter corresponding to the 3 field A, Y, Z, like this. And we can compute gauge transformation and correct gauge transformation like this. And this black part is completely the same as obtained from the AKSZ sigma model, but only the red part deformation of the AKSZ gauge transformation obtained from AKSZ sigma model. We have to add this term, and because of this term, AKSZ construction is broken. Right. Yes. So yeah, next part So you have. I want to comment the covariantization finally. Yeah, this is a local coordinate expression. So this is the statement. We assume Lie-algebra structure and DH equals 0. It is the assumption. And Then actual functional gauge invariant and gauge area closed. These two conditions are satisfied if and only if J is compatible EN form, right? Then Thomas already mentioned, but I want to comment about covariantization. We can cover and in order to obtain claim independent gauge transformation, we have to introduce connection, and we have to rewrite this local gauge transformation constructed by locally to global form. So we can rewrite this gauge transformation globally by introducing connection and E-connection. E-connection is defined by as follows. This is in other terms, this is another connection is defined on the algebroid, and this is like this. It is also called opposite connection. It's similar, but yeah, another map. Using connection and E-connection, we can rewrite the gauge transformation in covariant form. In order to write, this is we use this condition. E-connection is constructed from and normal connection like this. In order to write the gauge transformation covariantly, we need curvature. We need two objects. One object is so-called E-torsion, defined like this, and another one is so-called the basic curvature, defined like this. Basic curvature is related to the E-curvature like this. So using two objects, we can obtain like this. We can obtain covariantized frame-independent version of the gauge transformation like this. It is rather complicated, but anyway, non-trivial term is only last part. If H equals 0, this is completely the same as the AKSZ sigma model case, right? So we obtain okay, this is conclusion. Yeah, we consider the geometry compatible with the algebroid and the pre-multi-symplectic structure. And this structure has many examples. And we can construct topological sigma model, but it's a deformation of like a sigma model by best limit term, so-called best limit term, H term. And this is make sigma model completely consistent with the geometric structure and Hamiltonian mechanics, Lagrangian mechanics structure. So this suggests that we can construct the BFV and BFPV formalism of this sigma model. But it is not AKSZ. And BV formalism has been concretely constructed for the case of n equal to case by this paper. So yeah, we need more general understanding, more geometrical understanding for this structure and the sigma model structure. Future work with like this. And of course, we need some more geometrical the generalization of AKSZ construction in this model and other more generalization. And as I said, as an example, this is related to multi-simplex structure, so maybe related to multi-simplex reduction. And there's the possibility to quantization as a generalization of deformation quantization formula of Kontsevich. And this structure is a very, very special case of a general real algebra, so we can there's the possibility to generalize this model to general real algebroid. Yeah, thank you very much for your attention.